Hi everybody, today we're going to look at exponential growth and decay, and they typically work with problems that are either investments or population, and they typically don't involve linear relationships. They're an exponential relationship. So here's our first example. We've got $10,000 that's increasing at 5% per annum, where per annum means the growth per year, over 5 years. So it's going to compound 5 times. In our table here, we have a value of n, the amount at the start of each year, the amount at the end of each year, and an interest component. So at the start of year 0, we have $10,000. We invest the money and we get $500 of interest. 5 divided by 100 times 10,000. We add that to the original amount, and we end up with the amount for after one whole year. A0 plus 1 would be A1. So if we withdrew the money after having it in the bank for a year, we would get $10,500. So the next year starts. And at the end of that period, we take the $10,500, we calculate the interest on $10,500, which gives us $525, which gives us the first change from a simple interest problem, which looks quite similar to this, in that the interest now changes in each period as we recalculate the amount of interest to add, rather than with simple interest where we just would have added on $500 each time and only done the interest calculation once. So we add the 525 to this amount and we get our new amount of 11,525. According to our formula, that's the amount that we would take out after our A1 plus 1th year, so that would be from the 2nd year. We repeat this process until we get to A4 plus 1 or A5, which is what the answer that we're looking for, which is 13,341.63. And a bit anti-intuitively, whereas we think of this as the initial amount in year 0, this amount here is actually the amount of money that's in the bank after 5 years. And we can see that because we've compounded 5 times, once per year. This process is known as compound interest, and it's what the banks do when you put money in the bank. So if we're wanting to generalize that, we could let A0 be the initial amount, AN being the amount at the start of a period, AN plus 1 being the amount at the end of a period, R being the interest rate per period, and N being the number of periods. So I'll put it in a little table like this. N, AN times R divided by 100, AN plus the interest, which is just what we did up here. And then we can generalize that to say AN plus 1 equals the amount that we had plus the interest, which is what we did here. And then I we know is just AN times R divided by 100, that's this, and then we can factorize that and we end up with this formula here. So anytime we want to know the last column, we can just take the first column, multiply it by 1 plus R divided by 100. Now we can take that one step further. And if we have a look, we start with A0, then if we want A1, the amount at the end of A0, we multiply it by the interest rate, which is just what we did there. And for A2, it's just what we had before, times by 1 plus R over 100 again, which gives us this formula over here. A0 times 1 plus R on 100 to the power of 2. And if we want A3, we just do it again, and that gives us to the power of 3, so we can generalize that to, for any period, it's equal to A0, 1 plus R divided by 100 raised to the power of the period number. Similarly, if we have a decay problem, instead of adding here, we subtract, and it will go down instead of going up. So here's an example. A city's population of 15,000 is decreasing at 10% per month. What is the population after a year? Well, we have to be careful. This is in years, this is in months. So we're going to change the periods over to months. A year is 12 months. The initial value is 15,000. The interest rate is 10% per month. well, the interest, not the interest rate. Well, sorry, the rate, not the interest, is what I was trying to say, as a percent. So if we're looking for A12, which is after 12 periods, it would be 15,000 times 1, in this case minus 10 divided by 100, raised to the power of 12, just using the formula we established here. And that would give us 4,236 people. Now, this part of the formula can be a little bit confusing, so I've tried to make it a little bit easier for you here. A 10% increase would be 1 plus 10 over 100, which would be 1.1 to the power of n, times by A0. A 10% decrease would be 1 take 10 divided by 100, or 0.9. That's 0.1. A 5% increase would be 1 take 5 over 100, which would be 1.05 if you simplify that a little bit. And a 5% decrease would be 1 take 0.05, which would be 0.95. A 100% increase would be 1 plus 100 over 100, or 1 plus 1, which is 2. And a 200% increase would be 1 plus 200 over 100, which would be 3. Substituted into the equation. I hope that helps. It's a fairly in-depth example of how to get from a simple interest problem where this would just be adding on 500 each time to the more complicated compound interest problem. There's still one more step that we have to look at with regards to what happens when this figure here is different in a different unit to this, but we'll do that in a different slide. Thank you everyone, and I hope that helped.